Hi friends, so today we start Fortran tutorial lecture 7. Today I am going to discuss subroutines, which are one more type of Fortran subprograms. In the previous lecture I discussed about functions, so those are another type of Fortran subprograms. Now using subroutines and function can make your program much more clean, much more modular, and so this is something which is always a good idea to do. I am Dr. Ganguly. Now let us look again at the sigmoid function, which is widely used in neural networks and machine learning. And the sigmoid function is given by f of x is 1 by 1 plus e to the power negative x. And we are going to write a subroutine to calculate the sigmoid function. Now one of the things the subroutine does is that it returns to you values which are in the argument list. So in the subroutine, the argument list is very important. For example, in this particular subroutine, sigmod x goes in and fx comes out. Remember that in the function subprograms, what was happening is that the function itself was the value that was being returned. So in the subroutine, you have to give the values all in the argument list, the input values and the output values. So here fx is calculated as 1 divided by 1 plus e to the power minus x, and then the subroutine ends. So you have a subroutine, the name of the subroutine is sigmod, the arguments are x and fx, and the subroutine ends here, so you have to put end subroutine. Now to invoke the subroutine we use the call statement. So here there is a do loop, and in the do loop I am going from I is negative 5 to 5. I am defining xi is float of I, and then I am calling this sigmod subroutine. So here the subroutine is going to take the xi value and it's going to pass it here as x. It's going to then return the fx value as y to the subroutine. So remember that x and fx, whatever is going on inside the sigmod subroutine, these are the local variables, and xi and y are the global variables. So here I am printing this value out, and then I am getting this here in the output. So that's something which you already know. The format statement is printing out two blank spaces, and then it's printing out the float here. Now you guys of course should remember that in Fortran I would be an int, so I have to convert it to float here. So now let us put this program in the compiler. So you see here the subroutine is here, the main program is here, and then I simply run it and I get these printouts here which correspond to the different values of I which have been converted to xi, and then the sigmod function has been called. Now of course here we can take the simple value, for example corresponding to x is 0, and if I put that I get 0.5, so I can check it here that the value 0.5 is corresponding to the location x is 0. So this is what the subroutine does. Of course, in this case where you are using the sigmod subroutine, it may have been easier to use the function subprogram type. But just to show you the difference between a function and subroutine, I have created this example and run it here. Now the subroutines actually start becoming more useful when you have to calculate more than one value and return them. So let us say we want to create a subroutine which is named active, and here I want to take the input value x and I want to return sigmoid and RELU. So the sigmoid function is given here, fx is 1 by 1 plus e to the power minus x, and RELU, the rectified linear unit, also widely used in deep learning, AI and machine learning. That's given by fx is x for x is greater than 0, and is 0 in case x is not going to be greater than 0. So let's create a subroutine for that. So here the subroutine is named active. It takes in x, it returns sigmod and RELU. So the sigmod function is actually calculated just by using the expression which is given here, that is 1 divided by 1 plus e to the power minus x. And for RELU, what we do is we first set RELU to be 0, and if x is greater than 0, then we put RELU to be x. So essentially RELU is a function which is very amenable to any if then else or if and if type of statement, and it's a function which actually improved a lot of the algorithms in deep learning. So whenever you hear of deep learning, you are probably likely to use RELU there. So again, I use this particular do loop to call this subroutine. So here I call the subroutine, I call it active, and then xi goes in and ysig, yrel go out. So I can use different names for the variables here. I have to just make sure that I am following the different rules of Fortran, that is I, j, k, l, m, n are int and remaining are float if I have not defined them separately. So this subroutine should work. It should print out the value of y here, and then we'll see what we get. So actually I need to put in the values of ysig and yrel, which I have done in the actual program, and then I have printed it out. So I print out this particular set of numbers here. So you can see the first set of numbers which is printed out corresponds to the sigmoid function. So I'm using ysig for that. And the second list of numbers which is printed out corresponds to the RELU function. So I'm using yrel for that. So this is something very useful. The advantage of subroutine, of course, is that you can have many different variables in the argument list, and then you can return all those variables back to your main program. Now let's look at more realistic example. Let us again go back to the Newton-Raphson method, and today we are going to create a subroutine to implement the Newton-Raphson method. So once again, remember, Newton-Raphson method solves nonlinear equations of the form fx equal to 0. The algorithm is given by xk plus 1 is xk minus fxk divided by f dash xk, and x0 is the initial guess value which you need to start off this algorithm. So once you start with x0, it goes on, calculates x1, x2 and so on until the point it has converged. Now convergence will of course happen when xk plus 1 and xk become almost identical, or you can say that this particular quantity here, fxk divided by f dash xk, should become virtually 0. So that will of course happen near the root, because near the root fx is 0 by definition. So we are going to use the Newton-Raphson method on this problem here. Y is 3x minus x to the power 9. So again y is fx here, and dy by dx is obtained by differentiating this function. I am going to use the starting value of x0 is 1.5. Now, if you are unfamiliar with the Newton-Raphson method, you can look at Math Question Bank for the derivation. That's in my Math Mania playlist. I'm going to put it in the end screen and in the description box. If I don't, please remind me in the comments. So let's continue further and let's try to write a subroutine on the Newton-Raphson method. So I'm calling this subroutine Newton, and I'm giving it the input variables n max, x0, the small number here, and I'm getting out of it x out and k. So now I'm not interested in all the different values which are going to be calculated during the process. I simply want to know the output value, that is the root of the equation, and I want to know the iterations which were required to reach convergence. So let us start by setting xk is x0, which is the initial value, and I set the counter k to be 0. Then I go into the do loop. I is 1 to n max. Remember, n max is coming from the input list here. I calculate k is k plus 1, so I essentially update this inside the do loop. I calculate this delta value y xk divided by dy xk. I have to use these functions later. So remember, inside the subroutine, I am calling these two functions subprograms, or I am invoking them, because in the function we really do not call anything. And then of course I have this statement in pink that if I have converged, then I exit the do loop, or I update the value of x depending on the Newton-Raphson formula. So here xk1 is xk minus delta. Remember, delta is this fxk divided by f dash xk. So then what I do is, having calculated xk1, I put xk1 in xk and then end the do loop, and then I continue this do loop here. So after some time, hopefully this is going to converge if you have a good enough guess. And then at that point, I put x out is xk, that is the root which I am going to output out of this subroutine. Now, of course, this subroutine is going to require two functions which I have invoked inside it. So these functions subprograms are given here. They are the same functions as I used in the previous lecture. But in that case, we were not using a subroutine for the Newton-Raphson method. We were using the main program. So here the function is y is 3 to the power x minus x to the power 9. So the function y of x simply returned this function value. So in the function, what happens is that the value of x goes in and y is returned as the function itself. So this is very much similar to the mathematical function, and same thing is done here for the function dy. The function dy essentially has a code which calculates the dy value here. So dy is 3 to the power x into log of 3 minus 9x to the power 8. Remember, a log of 3 is the natural log of 3. So we are going to, of course, require a main program which is going to call the subroutine. So the main program will essentially read certain values, the value of n max, the value of the error, the value of x0, the starting guess, and then it's going to call the Newton subroutine to calculate the value of x out and k, which are two numbers we are interested in. And then it's going to print that solution. So the solution is going to be x out and k. Now, the interesting thing about the subroutine is later on I'm going to show you that we are going to create a condition where we vary the values of x0, that is the starting guess for the Newton-Raphson method, and we are going to check impact of that on x out and k. So these are some things which can be neatly done once you have a subroutine. Now let's put all these pieces of code into the compiler, then we can run it. So essentially you see the main program now is pretty small. There is a subroutine which is the Newton subroutine, and then there are these two functions which calculate the value of y and which calculate the value of y dash. So the interesting thing here is that the main program is calling the subroutine. The subroutine in turn is invoking these two functions, and then the output is being calculated. So I give the input values as n max is 10. I give the x0 is 1.5 and I want to converge to 5 decimal place, and then the output comes out very nicely. I get the converged solution here, and it takes me 7 iterations to converge. So that's something which is pretty nice. Now, one of the things which often happens in nonlinear equations is that you have many solutions. You can have a plethora of solutions, and these solutions are all known as zeros or roots of the nonlinear equation. So fx is 0 may have multiple roots or zeros. So in this particular function, we know that there are two roots. One of the roots is at 1.15082 and the second root is actually at 27. So I have shown these in the math question bank 5, so you can check it out, the exact solutions. So how do we get the second root? So what I'm going to do is I'm going to essentially run the Newton-Raphson code for a variety of input values. That's I'm going to run it all the way from 1 to more than 30. So I'm going to see, depending on the input guesses, where does the Newton-Raphson method takes me, and also it will be interesting to see how much time or how many function calls does it take to converge. So it's the same program as what we used previously, but what I have done is I have put the call to the Newton within a do loop. And here I have done something more. I have increased nmax to 50 because I actually found that in some cases the number of iterations required to converge was much larger than 10. And the whole thing is put in the do loop. Do I is 1 to 40 at increments of 3. So as you can see, it goes from 1 to 4, 7 and all the way so on. And every time the x0 value is taken as I into 1. So it's essentially taking values from 1 and then going on further here. So you can see that depending on the starting value of x0, I get actually different roots. At the initial points, all the roots are converging to the first root here, and the second round here they are all converging to 27. And you can see also the number of iterations varies a lot. Of course, what will happen is that when your guess is close to the minimum point, or rather I should say the root, then you converge quickly. So that is one of the things about Newton-Raphson method, that it works better if you actually know the answer. So since we know the root is somewhere near 1, then those points actually converge very well, and as you depart from that point, the number of iterations it takes to converge becomes much larger. But interestingly, when you reach near 27, you again start converging to 27. Now, there is a point here where this particular input value will have a big impact. Now, I have not gone into the details and seen it, but if any of you guys are interested, you can check this value out and you can report in the comment section as to what is the point at which the root shifts. That is, what is the initial guess at which you get the first root and then suddenly you shift to the second root. That would be interesting to know. So if any of you guys are able to get that, please put it in the comment section. Now let's get to the more useful thing in many cases in Fortran, which is how do we use matrix and vectors in the subroutines. So here I have got a program here which essentially calculates, or rather I should say creates certain vectors and matrices. So I am defining the dimensions here. So I'm creating x and y as vectors. A is a matrix. I am reading the value of n, which is the size of this particular vector matrix, and I'm going to then make these variables. So this is a piece of code which essentially lets you have variable size matrix, and then I'm going to run it for n is 3. So here, for example, you see I have a do loop, do I is 1 to n. I am saying that xi is I square and yi is I cube, and then I'm going to print these values of x and I. I should get these two vectors here. X is 149 and y is 1827. Note that these are the square and cube of 1, 2, 3. And then I'm going to also create a do loop where I get the matrix. So I create do I is 1 to n, do j is 1 to n, and I create aij is I into j into 2 and then print this matrix. So this matrix is going to come out to be this particular value here. So let's try this out and get the hang of how to create these matrices and vectors in Fortran. So I have put the code in the compiler and I have run it with input n is 3. And as you can see, I have got the printout of the vector x, the vector y, and the matrix A. So these are corresponding to these numbers. So now what I'm going to do is I'm going to create a subroutine which multiplies A and x. So let's try to do that. So matrix vector multiplication is actually a very important problem which we often do in many numerical analysis situations, whether it is optimization, whether it is machine learning, whether it is numerical computation. So let's try to do that. Let's try to create a subroutine. We are going to call it matvec, and matvec is going to multiply a with x and it's going to return y, and I also need to specify the size of this matrix A and the vectors x and y. So essentially this particular calculation y is ax is quite ubiquitous in math, and let's check it out. Now of course here one thing I should do is, since I am not really interested in y as an input, y is going to be an output, I just set y to 0, that is all the parts of y to 0. And so instead of doing that here, I create a subroutine. I call it subroutine 0. And subroutine 0 takes y and n, and essentially it sets all the values of yi equal to 0. So this is the very simple subroutine 0. So I invoke this subroutine here, and then I have this do loop or double do loop or nested do loop. And here I calculate yi is yi plus aij into xj. Now you can of course see that when you are multiplying a matrix with a vector, for example a with x here, you will multiply 2 into 1 plus 4 into 4 plus 6 into 9, and that's going to give you 72. So similarly here I am doing it like that, and I am going across these two loops here. Now this particular setting to 0 is important because you build up on this value here. So you have this yi equals to yi comment. So you have to set this y initially to be 0. You don't want it to have some kind of values which are lingering in the memory from some previous run. So of course we are going to need a main program which is going to call for this y is ax. So this is the main program which is based on the program I developed before, which was trying to create values for the different matrix. And here what I have done is I have removed the y part. So I instead call 0 yn. So it's going to take y and it's going to set it at 0. So if n is 3, y is simply going to be 0 0 0. 3 rows of zeros. Now I have the do loop here. Here I declare xi as I square and I declare aij as I into j into 2. So I'm going to get x and a as these two vectors and matrices. And then I call matvec a x y n and I print y. So this matvec is going to do the whole problem of creating y is ax, and I will get much cleaner code because of this. So let's do that. So I have taken ax here and I have put it in the code, and then I have run it, and I run it for n is 3. That is the matrix vector size is 3, and I get the output as y is 72, 144 and 216. So this you can check out by matrix vector multiplication, that this is how you multiply the matrix and the vector. So of course you see that subroutines and functions can give you modular code. They help you to write cleaner code, and they also help you to reuse functions and subroutines once you have developed them. So once you develop a subroutine, for example, to calculate y is ax, or you have developed a subroutine to do the Newton-Raphson method, you can use it for many different functions, you can use it for many different problems, and so you kind of have your own bank of subroutines and functions out there to do all these different tasks. So I'm going to give you a couple of homework problems to further solidify your knowledge. So what you can do is that you can write a program with subroutines and function to solve the nonlinear equations using the secant method. Now, in my previous lecture, I discussed the secant method using only functions. So what you need to do here is you need to go and look at the Newton-Raphson program and modify it to some extent to write this particular main program which calls a subroutine. We can call the subroutine as secant, for example, and then it can call a further function y and then solve the problem using the secant method. Remember, secant method will not require the derivative function, so that's something which is useful. Also write a program with a subroutine which multiplies two square matrices. So essentially this is another important problem as far as linear algebra is concerned whenever you are doing numerical programming. So create this particular subroutine which multiplies a into b and returns the matrix C. So this is going to be a very useful exercise for you. So I'm going to stop this lecture now. So today we figured out several things. We figured out the very important concept of subroutines. Remember, subroutines are useful for returning more than one value, and they return the value through the argument list, whereas what functions do is that they return the value based on the function name itself. So there are of course certain situations where functions are very useful, but there are many more situations where subroutines are very useful. And so if you see most of the more modern Fortran code, you will see a very widespread use of the subroutine subprograms.